Let's talk about killer robots. How's that for a beginning? Just kidding. We're talking about leveraging AI in wireless design and operations. Interesting enough, actually the first thing that comes to many people's mind when we talk about AI is actually killer robots. So there are a lot of highly educated, smart people who are afraid that the singularity will catch up on us without actually us even noticing. So Elon Musk is one example of those, right? So I don't actually believe in that. I think it will take much, much longer than that. It will take a decade, probably 2 decades before we can reach that level of intelligence in the systems that we have built. Why? There's an inherent limitation in the way AI learns. So the way it works today is that you feed the training data to an algorithm, and based on that training data, the algorithm learns how to react and what kind of output to produce. So as an example, you have here an image recognition algorithm. So you feed pictures to it, and it learns to recognize animals and things. But when something changes in that starting point, it doesn't know how to deal with the change, right? So this is a pretty famous example. This is a sticker that the Google engineers made just for fun. So this is a shiny sticker that looks a little bit like a toaster, but not exactly. And when you place that right next to an image, most of the image recognition algorithms freak out. So 70% of the algorithms think this is now a toaster. So there's a really famous scientist, Josh Subenjo, who's actually studying this. It's called meta-learning and transfer learning. So he's basically studying and researching how learning process could be repeated. So how the algorithms are actually, he's studying how the algorithms learn. It's really stuff, but if you are interested, you can Google that. It's good to know that he's taking care of it. So because of this, I actually think that instead of killer robots, the AI is more like a minion today. A set of minions, right? So they are mostly friendly, they're really hardworking, they don't require salary, and they can actually do most of the tasks that the human being can do in less than 10 seconds without actually thinking about it. If you've seen the movie, you know that you can't let the minions run by themselves. They need a master. You need to watch what they do, otherwise it will lead to a chaos. You can't give them weapons, of course. That will lead into a bigger disaster. But they are really useful helpers. So I've been researching this topic for more or less past 5 years. I'm doing a PhD on automation of wireless network operations by using machine learning and deep learning. And today, I wanted to give you an overview on some of those minions that I've actually either used or I've seen during the research project. And I divided those into 3 categories. So we have the data acquisition and preparation, and then network design and optimization, and then monitoring and assurance. So let's start with the data acquisition and data preparation part. So many of you are familiar with machine learning, and there was a deep dive also during this event. I guess one of the first things you have been discussing in those kind of courses is that in order to get started with machine learning and deep learning is that you need a lot of data. You need a lot of data, it has to be clean, and it has to be well organized. So if you want to move and use more developed supervised learning algorithms, you also need to tell the algorithm what the data is all about, right? You need to label the data. And sometimes that's a massive work. You need to label thousands, millions, tens of millions of rows of data. But the good thing is that there are tools for that. So, for example, classification algorithms can be used for doing that. I've been using decision tree, random forest, KNN algorithms like that to actually group the data for me. Another more Wi-Fi related use case is extrapolation of the data. So you can actually learn the RF environment. You can do surveys, and you learn basically the attenuation and the noise level and the spectral conditions. But you can actually use machine learning or actually deep learning algorithms like artificial neural networks to transfer that data or simulate it into a different frequency band. And that's very handy. We'll come back to this a little bit later in the optimization part. Then the third example is something that we actually built at Ekahau. So we have a new feature in Pro 10.1, which helps to create automatically the floor plans in the planning phase. So it's a convolutional neural network basically that reads an image and then creates a digital floor plan out of it. And before somebody asks, I go ahead and admit, yes, you can fool even this algorithm with the same sticker. So I placed it in the middle of the living room. The algorithm didn't go bonkers. It doesn't think the whole building is a toaster, but it did create 2 extra walls in the middle of the living room. So the second set of use cases are more related to network design and optimization. So basically, most of the deep learning algorithms are actually dealing with optimization. So how it works is that it takes the data in as vectors, and then to simplify grossly, you can visualize it in a way like in the picture here. So this is a 3-dimensional space where you have a small set of variables, and then basically you can use this kind of a plane to search for minimum and maximum values. Now, a deep learning algorithm can take millions of parameters, and it can optimize all of them simultaneously. So obviously the illustration would be much more complicated than this. So then you might ask, why is this interesting and why is it useful? Well, for example, when you're creating predictive models, when you are estimating path loss or predicting the signal or creating predictive signal propagation models, the algorithm will actually go through every single permutation. So every single combination of the parameters, and it will give you the optimal output. So this is very useful when you test, for example, or you simulate network configuration changes, or for example, you do capacity simulations. And the interesting thing is that now when we go back into the extrapolation of the data, you could actually, if you do a good survey on 5 gigahertz, you can actually use the data and you can simulate an optimal 6 gigahertz network even without visiting the site by using the data that you have previously collected. Another example is end-to-end optimization. So many people who are working with 5G projects seem to agree that 5G can actually never meet the hard requirements for latency and coverage and throughput at the same time. So the more likely outcome is that there will be more and more hybrid networks combining different access technology with IP networks with mobile core. And in this kind of environment, it's going to be really difficult to understand what's the end user performance and what end user experience. And again, you could actually use deep learning to model that end-to-end performance and use that information to, first of all, map the end-to-end connectivity across the different networks. And then based on this, you start looking at different configurations in order to optimize then, for example, throughput and latency for the end customers by using the configuration on the access network. But again, this is not the master. This is the minion, right? So I don't think we are anywhere close that we could do fully automated network planning simply without just trusting on the mathematical methods. So this is a tool to aid and to combine with more traditional design methods. Then the third example I wanted to give is network monitoring and assurance. The typical approach to network monitoring is anomaly detection. I think MIST was presenting their monitoring solution in this event, and they were talking also about anomaly detection. So it's basically baselining. So you feed temporal data to the algorithm, and it baselines the typical performance of your network, and when something abnormal happens, it actually gives you an alert. So this example here is from AWS. They actually have productified the algorithm in a way that you can actually do an anomaly detection model without writing a single line of code. So if you want to analyze the packet loss in your network, you just feed the data, and it will alert when something abnormal happens. The next step from this is start finding patterns in the data. So you do sequence clustering in the data. Once you understand the patterns, the frequency of the patterns, you can analyze the causality and the correlations within that data. And again, with that data, you can actually start predicting things happening, either good or bad things happening in the network. Another example that I've seen is related to real-time spectrum monitoring. So I've seen some solutions which are actually capable of performing spectrum monitoring 24/7, and you can train the algorithm to actually recognize interference automatically and also classify the source automatically. So that was a few years of research in 10 minutes. Hopefully it was useful. If it wasn't, I don't really care. There's no time for questions.